Hello, today I will present multi-agent racing simulation project. In this project, two racing cars compete on a dynamically general track, with one car controlled by a classical Qlearning agent and the other by a DQ network. Our project not only demonstrates modern reinforcement learning technique, but also evaluate their performance in a complex dynamic game environment. Let's dive into the code and see how it all comes together. First is our racing track is generated dynamically using periodical functions. This segment of code uses sine and cosine function to simulation curves and undulation in the track. Notice here in the function row center value, we determine the base center and then add irregularities. The function get track offset and get track half width compute how the track shifts horizontally and varies in the width depending on the car's programs allowed along the track. And here we have our drawing function and the racing car class. In draw car function, we render the car as a polygon with addition details like windows and wheels. The racing car class defines the car's characteristics such as speed, dimension, and the moving logic. For example, the update method calculates the reward based on vertical programs and apply bonus or penalties according to game mechanism. And this part of code set up the multi-agent racing environment. The multi-agent racing environment class manages the game loop in the initial agent method. Two racing cars are created with distinct starting position. The step function handles agent update, calculate reward including bonus for overtaking and penalties for leaving the track, and update the game state. Finally, the draw method visualizes the environment, drawing the dynamic general row and the finish line. And about the Qlearning method, we create a classical Qlearning agent. The Qlearner class maintains a Qtable where each state discretized here by running to one decimal place is associated with expert reward for each action. Using the epsilon greedy strategy, it balances exploration with exploitation. The learn method applies the standard Qlearning update formulation to iteratively improve the policy. And in contrast to the tabular Qlearning method, the DQN agent uses a neural network to approximate the Q values. The DQN class builds a forward neural with input, hidden, and output layer. The relay memory class store past experience, enabling experience replay to reduce correlations between samples. Finally, the DQN agent class includes method for selecting action using an epsilon greedy policy, optimizing the network using mini batch and periodically updating a target network to stabilize learning. And for the training and evaluation, in our main training loop, we train both agents over multiple episodes. Each episode, we set the environment and both agents interact with the game by selecting action based on their policy. As a simulation progress, we record cumulative reward, performance score, and converse data. After training, we plot the following evaluation curves. Now we run this program. We can wait a moment. We can easily see that there are two cars in the race. Car 0 is the Qlearning agent, and car 1 is the DQN agent. In the first few dozen training cycle, the DQN agent, the both car agent can't pass this racing, and we can see the detail in the table, and we can see that Qlearning reward and DQN reward also have some progress. And let's see that they are training for some epoch. Oh. But you can see that after training some fewer cycle, we can see that the DQN agent can pass game. And for demo purpose, I directly save the curve graph of 240 and 1000 training cycle epoch. We can see from the curve graph like this one, we can see the convergence table and stability. The report noticed that while Qlearning convergence steadily, it doesn't reach the high peak rewards of the DQN, and our convergence curve below from the delta changes in Q value update and DQN loss clearly show this behavior. And about the ROC curve, the DQN achieve a higher success rate in the overtaking and finish, which is reflected in our visualization. Although the DQN has fluctuation, it learns faster and it should be higher cumulative reward. And we can see the training set, and the evaluate demonstrate that DQN generalize better on unseen data compared to Qlearning. This is directly observable in the performance score generated by our simulation. And we can see the validation set. There are also DQN almost have the high peak, the high score, and the Q performance is also the less scores. And we can see the learning curve also like the training data set. Also, but Qlearning maybe see more stable than DQN agent. And in conclusion, this project successfully integrate class code Qlearning and modern deep learning approach via DQN in a competitive multi-agent racing simulation. Despite challenges such as training instability with DQN, our robust code architecture including experience relay replay, target network update, and careful reward shaping, and improve in the DQN agent. For those interested in review the full code and details documentation, please visit my GitHub. Like this, you can save this link, and I will post my report later on this GitHub. And if you are interested in this project, please subscribe. Thanks.